Thank you everybody for joining us today. I'm really excited to be speaking at the Kubel Data Lake Summit 2020. My name is Knapp. I am the co-founder and CEO of Ascend.io. I'm really excited to talk about the design and creation of intelligent orchestration for data pipelines. I have a long history and background with data pipelines and data engineering. I actually fumbled into a data engineering career in many ways back about 16 years ago. I was a front-end software engineer and ended up finding pretty quickly that I was spending more time writing data pipelines than I actually was writing front-end code. And I've spent really the majority of my career creating data products, data teams, data companies over the last 15 plus years. Have led 60-person data engineering teams as a founder and CTO of a larger tech company, and have also spent a lot of time building data pipelines and working with a lot of the early stage technologies. So to give you a quick little bit of background just around Ascend and really what we do and where we fit, we love data pipelines. We're a group of data engineers who spend a lot of our time both before Ascend and now at Ascend, figuring out how do we make more data pipelines, how do we do them faster, how do we do them easier, and we've been at this for a number of years now. And so what I really want to walk everybody through is, what was our core challenge in building of our product, which was how do we actually enable smarter pipelines and less code? Everybody loves being able to accomplish more for less, and software engineers and data engineers, the biggest measure that we oftentimes see is how much code does it take for us to have to write to accomplish a certain goal. And when we spent a lot of our time and our careers in writing of data pipelines, one of the things we really started to figure out was, gosh, we seem to be doing the same things over and over and over again. And in fact, we should be able to automate and alleviate a lot of the pain that we've been experiencing as data engineers by creating smarter pipelines. And that's really where we're going to spend a lot of our time today, is talking about how do we actually create these smarter data pipelines. So to do that, really want to spend the first little bit of time talking about the TLDR of data pipelines. And more specifically, what is the very basic notion of a data pipeline? Where do we fit in the architecture? And then why are they so darn hard, right? And oftentimes it starts with the data pipeline hello world. Right? We have a lot of really cool tools in and around our ecosystem. We have these great machine learning products and data science products and BI products and warehouses we want to go get data into. And more often than not, we're trying to write a data pipeline because we're not only moving data around, but we're transforming it. And that hello world seems really compelling, right? Like, okay, I got to schedule a little bit of stuff. It's going to run my code on some cadence, some timer or some trigger. It's going to take that code, it's going to push it down to Spark or some other engine, and we're going to process a bunch of data. We're going to store it inside of S3, GCS, Azure Blob Store, you name it. And eventually we're going to take some derived data set and we're going to pump it out to one of these other things, right? Classic data pipeline paradigm. And it seems pretty simple and straightforward. It definitely did in my career. And what we have all started to experience, which I'm guessing if you're listening to this, probably have also started to experience too, is the real world is a little bit more of a more complex world, right? That box of just a little bit of simple code actually ends up being far more capabilities and sophistication we have to build into our data pipelines. We actually have to start to do some of the basic things. Like when we first start creating those pipelines, we have to deal with a lot of things like data ingest and formatting, dependency tracking. Once you're using tools like Airflow, does a pretty good job of executing the DAGs, the directed acyclic graphs for you, and so on. Then we also start to do things like Spark optimization. What are the right parameters that we should be sending to each and every single Spark job? Do we know how many executors or how much memory it should have? Things like that. And then, of course, error handling. If data is moving through and something fails, is it recoverable? Is it not? Etc. But that's only the start, right? After we get through some of those basics and we increase our level of complexity of our data pipelines, we often start to introduce this next intermediate layer. Things like data profiling. If we start to profile our data, we can make our pipelines even faster and more efficient and more optimized. And if we're building a lot of them, they're probably getting expensive. right? So we want to tune that. We want to do things like incremental processing and things like intermediate data persistence. So we're not having to process as large of volumes of data as frequently. We also are looking to do things like data and job deduplication. That becomes incredibly important when we're doing a dev to stage to prod style approach to data ops, where we may be doing very similar duplicative work all over our ecosystem, but we don't want to actually have to duplicate the work, right? So when we start to optimize and we get into this intermediate stage, there's a whole other set of capabilities we end up building into our data pipelines. And then the third level that we oftentimes get to, and this is really when we start to get into larger enterprise level requirements, are things like the data and code integrity. Does the data we have sitting in our warehouse, our lake, actually map to the code and the upstream data? Can we guarantee with mathematical certainty that we have the right data in the right place? And moreover, can we also guarantee that if we're not supposed to have data, that it's no longer there? Are we garbage collecting our old data sets? Or are we leaving our company open to GDPR infractions or CCPA and the others as well? Similarly, are we doing lineage tracking? If you're in finance, for example, you need to know and be able to prove that this piece of data went through these transforms and can survive an audit, and that it actually was derived by running this code on these upstream pieces of data. And can we guarantee that? What happens if somebody changed the code? Do we know when they changed it? What data set was generated from that? Is all the data that we're working on now working off of the right version of that data? So that becomes super important. All the way up to security and governance. Are we making sure that the right people are accessing the right pieces of data and no more and no less, right? And so all of a sudden, that really basic hello world becomes pretty complex. And what we find is that this world what we were originally working in, this world of, hey, I just want to write a little bit of code, ends up being pretty complex. And we end up spending the vast majority of our time, 90+% of the time in code we write, is actually tied to this stuff as opposed to the logic that we want to apply to the data and applying our context and our business logic to that data. So all of a sudden, we really start to miss Hello World, because that seemed really simple. Hello World seemed fantastic, and it was really fun and exciting to get started on it. But this whole world of data pipelines really starts to become pretty painful and complex. So we wanted to go fix that. And so when we think about how do we go solve this problem, how do we actually build a more intelligent orchestration system, there's some really key questions that we end up asking ourselves as data engineers every time we build a data pipeline. And the questions boil down to some pretty basic things, which is, I have code, I want to run my code on my data, so when do I run it? And that usually then begs the question of, did I already run this code on this piece of data? If so, do I need to run it again, or is it safe not to? Did any of the data change? Did any of the code change? Because if they did, I probably need to run my code again, but I need to know whether or not that happened. And then the entire stream down from that is, well, where did this data go? And do I need to do the same set of questions for each incremental stage downstream? And it's funny because these seem like really simple and basic questions, but the lion's share of the code we write is actually to codify our answers to these questions. And this is really where we're spending most of our time. So we took a bit of a step back and said, like, this seems crazy. You know, oftentimes when we're using databases, we don't have to deal with this, right? We can literally just write a really cool SQL query that are probably more complex than this usually. And it pumps it through the millions and millions of lines of code inside of our database, and boom, we get results, and everybody's super, super happy. So what's really missing here? And what we figured out was, well, there's no equivalent to a database engine. There's processing engine. We have Spark and Kafka and Presto and all these other great tools that process the data. But what there isn't is a query planner and a query optimizer, something that can be continuously running because our pipelines are continuously running, that is solving for this. And as a result, what we end up having to do when we write data pipelines is we are manually designing a query plan for every stage, every pipeline. And the maintenance burden and the complexity expands greatly every time we increase in order of magnitude and scale, or dependencies, or the nature of the data changes. And this is why even the most basic things we may be trying to do to our data with data pipelines can be incredibly costly from a time and maintenance perspective. So we took a little bit of a step back here and said, well, why is this? And like, what do we get in the ecosystem today? And what we really started to notice was there's a couple of evolutions of these orchestration technologies, right? These scheduling systems, these pipeline designers that we've seen and have used many of in our careers. And we noticed that there'd really been this evolution from this generation one, which is much more of a raw, like I go write code and it works on timers and triggers and it will run my code, to solving one aspect of ease of use, which was more stassified, oftentimes hybridizing code with UIs and even templatizing a lot of the code that needed to be generated to run. And what we noticed was there was a great change in paradigm here that made data orchestration and data pipeline orchestration easier to use, actually reached more people. But the thing that wasn't getting solved for yet was the scaling how many systems I have and the interconnectedness and the dependencies between those. And so what we found was oftentimes these second generations made it easier to write some pipelines, but they didn't make it easier to really go at massive scale and complexity for modern data pipelines. So we spent a lot of time looking around the ecosystem for ideas. We were software engineers. So our typical stack starts with React and Redux at the top end, goes through a bunch of microservices that are all run on Kubernetes, that sits on top of infrastructure that is terraformed. And all of a sudden, we started to find a few patterns that were really interesting for us. And one in particular was this move towards declarative engineering. To put a pretty specific point on this, declarative programming allows us to actually express the logic of a computation without describing its control flow. The fundamental idea behind this is how do we minimize or eliminate the side effects by describing the end state, what we want to accomplish, as opposed to how to accomplish it. Put another way, in far more simpler form, it is describing how versus what. In a declarative paradigm, we move to the what. It becomes more compact, clear, easier to maintain, and has tremendous benefits. React is declarative. Kubernetes is declarative. Terraform is declarative. We see some of the most powerful technologies as software engineers today moving towards declarative paradigms. SQL is declarative. So we thought about this and said, well, how would this look if we took our paradigm for pipeline orchestration? What would this look like? And what it starts to do is it inverts the paradigm. It says, let's actually take the code and the data logic that we write, and it should sit on top. It should actually be directing the control plane, as opposed to having some orchestration tool, as opposed to having a scheduling system running our code. Because that imperative model puts a huge burden on us as software engineers, whereas a declarative model can put the burden on the control plane and make it the control plane's problem to figure out things like state changes, error recovery, and so on. And so to go a little bit deeper into this design paradigm, when we look at imperative versus declarative, we find this pattern emerge, and it emerges across a number of different fields, as I've mentioned. And the pros and cons usually shake out pretty cleanly, which is in the imperative model, we get max flexibility, high levels of control, but we put a huge burden on ourselves for state management, dealing with the assumptions that we bake into our code, manual optimizations, dealing with integrity checks, failure management. All of that is the responsibility of us as developers. Whereas in a declarative model, the benefits are far less code, faster dev cycles, adaptive to change, and less maintenance. And we get those benefits because we're pushing down to a system. There is a system that is responsible for all those things that imperative systems have to deal with. The downside is really that we have to be able to support annotations that override automated behaviors. Oftentimes, the developer, the user of the system like this knows something that the automated system, the control plane, just simply can't grok or doesn't know about or hasn't been trained to do. And as a result, you need the annotations to override behaviors. And second, and this is where we'll spend a lot of our time, is declarative systems require domain-specific control systems. They need a control plane that takes these higher level constructs and is able to execute on those constructs on behalf of the developer. And that's really where we're going to dive into, is this notion of building of this control system. Diving into this was a really interesting journey for us, because when we started, we kind of felt like the gnomes from South Park, if there's any South Park fans out there, which is, hey, we want to start with declarative pipelines. And we think that these are going to be pretty cool. And phase 3 is going to be profit. And we weren't really sure what phase 2 was yet. Like, how is this really going to actually work? But we were pretty sure that if we get there, it'd be awesome. So we did what a lot of engineers did and we started to make a list of what should a good control system do. As avid Terraform, Kubernetes, and React developers, we had a lot of frames of reference. We have had huge, long experiences with building of data pipelines from Kafka to Storm to Spark to Hadoop. And so we pulled a lot of that together and said, well, what are the things basically we don't want to do anymore? What are the things that aren't fun to do as data engineers, and we should be able to get a system to just do this for us? And the list we came up with was pretty exhaustive. It was a big, long laundry list of all sorts of different things. Hodgepodgey, really hard to structure, but there's a lot of, gosh, if a system could do this for us, life would be much better as a data engineer. And so what we did was we put it within this structure that I described a little bit before, this move from imperative to declarative, and tried to actually break it down into some simpler pieces and say, well, what does this really boil down to? And what it boiled down to were these three things, which were this notion of data awareness, the notion of autonomy, and self-optimizing. And so when we think about that, data awareness, autonomy, and self-optimizing, if it can execute to those items and fit within these categories, we might have something that really can help us build smarter pipelines that will do a lot of the most painful stuff for us. And so that's where we're going to spend a lot of the remaining parts of our talk here, is going into these three categories with a bonus category in there too for fun, geek factor. And so when we put more of this against this backdrop, and declarative, where we're going to spend a bunch of this time now, is on the control plane and how it delivers on these. So as a reminder, we're going to think about this world in three layers in this declarative construct. A logic plane. A logic plane is the code we write that defines the what. The what can be things like source data from this system. It is of this format. We don't have to specify how to source it, when to source it, what to do with it, but just what it is. The control plane, where we're going to spend a ton of time, is this system that is automated that determines the how we execute on the definition of the logic plane. And then the execution plane is the system that does the work. The execution plane is, in most of our contexts, Spark, or also Kubernetes, because we run a lot of Kubernetes too. And it is the system that is grabbing data off of storage system, processing it, doing all the work, executing to the instructions of that control plane, and fulfilling the what of the logic plane. Diving deeper into the control plane and going back to those three categories plus the bonus one, the scalable bonus category that I've added in for fun. These are really the three, now four categories that we care about for a control plane. High level, it needs to be data aware. The system must fundamentally be able to track all data for all time, including the profile of the data, where it came from, how it got there, where it went to, and how it was used, and why. Without that as a backdrop, we can't really deliver on the other promises. We need to fundamentally know so much more in this system. The second piece is autonomous. It needs to be able to adapt and watch for changes to both data and code and dynamically generate the work required to fulfill this logical model. can only be autonomous if you're data aware. Without that, it's very, very hard to be autonomous. You can be automated, you can be scheduled, but you can't be autonomous without broader context. The third piece that I added in here, because it becomes very important to the autonomy, to make the autonomy work at scale, is you have to be able to do this where you can track trillions of records, billions of data partitions, and react to changes within seconds. It's easy to go and generate a few hundred or a few thousand Spark jobs a day. It's much harder to track those billions of partitions and analyze the 2% that has changed within 5 seconds and figure out what then has to be done to update those data partitions. So the scalability matters immensely. And then lastly, self-optimizing. If we have all this data that we're tracking about moving through the system, all this metadata, if we're dynamically and autonomously adapting to it, and we can do these things at scale, well, we should be able to actually self-optimize. We should be able to do the things that we have had to do as data engineers to manually tweak and tune. We should be able to then automatically optimize how data moves through and do all of the tricks that we used to have to do very manually. And hopefully, over time, the system gets so smart and so good at this that it can even outperform us at a lot of the tasks that we used to have to manually tweak it to. So we'll talk about that. Sure, everybody's really eager now. How does it work? And to do that, I'm going to give a quick reminder. Remember these 6 questions, because we're going to come back to them a few more times. When do I run my code? Did it already run? Depends on, do I need to run it again? Do I need the data change? Do I need the code change? And then how is it used downstream, right? The control plane, if we don't have to answer this as a developer, the control plane has to be able to answer that for us. So let's keep this against the backdrop of our mind as we go deeper in. And we're going to start with data aware, which basically boils down to track everything. Data aware really comes down to not just tracking at a component level, right? At this logic plane, yes, we have on the logic plane, we have our components. They're defined by a location, a schema, some code, and it's a pretty simple construct. It would be close to a box if you were in the DAGs of an Airflow DAG. But beneath the component is where it really starts to get interesting. Beneath that component is where we track every fragment of data that is underpinning it. And a fragment we generalize. It is a partition, but it may also be a partition that doesn't actually have partitioned logic yet. It is just a piece of data. And a component can have millions or billions of pieces of data if necessary. And what we track in there is a fewfold. Obviously, we track where it's stored, and that's going to become really important because we store it in a very specific way that gives us a huge amount of advantages. And we'll get to that a little bit later. We, of course, track the data SHA because we want to know if that data has changed, and that will come in play in a little bit too. But we also track a few other things that become very valuable in understanding how to use each and every single fragment of data. First is we track the data profile. These are pretty basic things at times. These are things like the schema, the min, the max, the cardinality, the lineage of the fields, what code generated which field. And this becomes really, really important because knowing that profile of data helps us do a lot of really smart things downstream. It helps us know, for example, when we're running code on it, if we're doing a map style operation, a one-to-one on partitions versus a reduction, say going from hourly data to daily data, it helps us quickly assess the inputs. So tracking this metadata makes the system much, much smarter in how it makes decisions. The second additional piece we track is the job that generated the work. Knowing the statistics that applied and generated every single piece of data, every fragment, not at the component level, but actually at the lower level, every fragment. What engine produced it? Was it Spark or our Go workers or some other system? Was it, what were the input fragments? What were the output fragments and where did they go? We track the SHA, not just of the data. That's easy. We actually SHA the code, and that's going to become super important in a second. We track the start and end times. I actually track a bunch of intermediate times too. And we track the resources. How much CPU and memory were given to the drivers, the executors that's running on an external cluster, how many resources that external cluster used, etc. We track tax times and a bunch of other neat stuff too. Then the third piece, and this becomes really part of the magic, and we're going to go deep into Pshots in the next session because this is the key to the autonomy, which we calculate what is a partition fingerprint. A SHA is a fingerprint. It's a collision-resistant, mathematically secure and sound way of quickly saying, I have a bunch of data and I need a unique identifier for this data, in essence. And this Pshot that we track is a recursive SHA for a source piece of data. It is just the data, the data SHA itself. But for downstream fragments of data, it is the combined SHA of the code and the upstream Pshots. And it recurses all the way up. And this becomes a really unique thing that helps us uniquely identify all of the data that has been stored and all the calculations we have made. Now it's going to become really important. So we're going to dive into that next. But for this piece here, it all boils down to tracking a tremendous amount of data. And this is one of the reasons why being plugged in at the orchestration layer between code and execution as a control plane, you are in this perfect spot to collect all of this data as you can see everything flying through, and then you have the ability to act on it, which is what we're going to talk about next. Let's talk about the autonomy layer, the ability to respond and adapt to changes. As we talked about in the previous section, the beauty of change detection is this Pshot. The idea behind a Pshot for any piece of data that is being stored, we know the component and the individual fragments of data and the Pshots of those individual fragments. And this becomes incredibly powerful because what happens when something changes is we now actually get a mismatch between the Pshots of what's been stored and what we expect to be stored. So when we start with a component, what can cause that component Pshot to change? Pretty easy. For source data, schema changes, if the data SHA of the file changes or some other partition of data changes, those will trigger changes. For a transform of data, if the code changes, we're SHAing the code, so the SHA changes. And this becomes really powerful because it's a very fast way of doing change detection all the way at the logic layer. But what about pipelines where oftentimes I just have a new piece of data that's coming through? If I have a new piece of data coming through, the SHA of my component isn't changing. I didn't change my code. I didn't change my schema. It's just a new file, for example, that showed up that I now need to propagate through. Well, this becomes really interesting because what now happens is I have new fragments that show up. Those fragments have SHAs, and there's potential downstream fragments for those. And so a great example to show up this is a very simple use case where I have two components. One's reading from the other. If the file upstream changes and its data SHA changes, even if the code hasn't changed, the downstream Pshot now changes because the data SHA changes. And so when I'm looking at what I expect for there to be stored, the Pshot that I expect to be stored, and I look inside of my object store and I find a different Pshot, our system is able to detect those changes. Now, of course, we're doing this not just by looking inside of the object store. We're storing all of this in a higher level memory-backed store where we can very quickly do this at incredible scale. But this gives us the ability to rapidly do change detection. Now, you may ask, well, how do I actually know the inputs? For example, if I'm doing this downstream propagation of data, how do I know what I actually depend on? And this comes back down to that data awareness aspects that we talked about. First is the profile of data. By tracking the min and the max and the cardinality and the distribution stats of our upstream data sets, and then by parsing and analyzing the SQL or using annotations for languages like PySpark or Python or Scala, we then get enough hints about how the system behaves that we know when you have upstream data, what conceptual downstream partitions they affect, without having to look at all of the data, without having to even actually look at the underlying data itself and analyzing it, because we're storing all of that in our database and our metadata stores. And so in doing so, we're able to do this very quickly and calculate the SHAs of what we expect and what exists, and in doing so, know what doesn't match and generate the work required. It's in many ways oftentimes why declarative systems are described as being in this constant state of repair, because they're constantly looking for what doesn't match. And when they find something that doesn't match, they generate the work to fix it. How that ultimately works here is when I have a read connector, all it's doing is just constantly looking for new data. And when it finds it, it ingests it, it profiles it, stores it as individual fragments. It's a pretty simple job for a read connector. Similarly, at a transform level, what I'm doing is I'm constantly evaluating. I'm looking at my code. I'm looking at my upstream code and my upstream data. And I'm just looking to see if those SHAs change. And what happens is, like, if I change my code, I know that every underlying partition and fragment of data doesn't match. And so I can be smart enough to say, oh, I should probably go backfill those changes. Very similarly, if I just have small bits and pieces of that data change, I can figure out just the individual fragments and partitions of data that need to be updated and generate the work for just those without having to do some big, massive backfill. Similarly, at the fragment level, lower level, for those read connector source fragments, the math becomes pretty simple. If a new fragment shows up, odds are there's a downstream fragment that either needs to be updated or potentially a new downstream fragment. If I updated something, I definitely have an update that's required downstream. And if I deleted a fragment and that deletion needs to be propagated, you can with near certainty, guarantee that there is a downstream fragment that also needs to be updated. Pretty similar patterns happen at transforms too. Same thing, if something changes and there is a downstream component, almost certainly there is then a downstream job that needs to be generated. And so this is how the declarative control plane model works, is the entire system is just constantly generating Pshots, just over and over and over again, generating Pshots and looking at what it expects to be there and what is actually there and figuring out what doesn't match and generating the work. It's funny how what can be incredibly complex systems can actually boil down to something that is a pretty simple concept like that. Implementation details obviously hard, but it's a pretty basic concept. And so when we put this against the backdrop of those 6 questions that I posed earlier around writing of data pipelines that we have to answer these questions for, it becomes pretty simple, right? When do I run my code? Always. Just continuously evaluate. We're just constantly looking to see when we have to run code. The entire next batch of questions boils down to a single answer, which is check the Pshots. Did I already run my code? Do you already have a Pshot for what you expect? Do you need to run it again? Only if the Pshots don't match. Did any of this data change? Did their Pshot change? Did any of my code change? Did the Pshot change? Basically, all boils down to check the Pshot. And if you can calculate this Pshot very, very efficiently, you can run a highly efficient pipeline. Then the last piece, how is this data used downstream? Traverse the graph in the fragments, look at the job statistics, and rerun Pshot calculations over and over again. Now, for those of you who have done a lot of SHA calculations in the past, you'll know that one of the things that can be really hard, however, is how do you create large numbers of SHAs very, very quickly, especially when you're tracking up to 1 billion partitions of data. A lot of this comes down to the finesse, because obviously you don't want to be calculating billions of SHAs every minute, as it's incredibly inefficient. And so there's lots of tricks you can do that actually help you scale to trillions of records, billions of partitions, and millions of Spark jobs a day. And they boil down to a few things. At the core, you want to detect changes efficiently. So let's take this example we have of the 3 planes here. Underneath 2 components, there is a tree structure that we're able to create. And this tree structure is really powerful because when we start, right, because we're analyzing all the partitions of data, we know that the December 31st, 2019 data for component A is actually the only upstream partition of data required to generate the downstream December 31st, 2019 partition for component B. Right? And because we know that, we can calculate and analyze those And we can even cache some of the results and so on to make it faster. But it's already 2020. Every time we're running a scheduling cycle, we don't want to have to traverse all of component A and component B's 2019 Pshaws and calculate and generate those over and over again, because it's really unlikely that that data is changed. So we fall back on a couple of things that make this much easier. First, we do more SHAs. We do lots of SHAs. We do SHAs of SHAs of SHAs, and we do them at multiple dimensions and layers. The other thing we do is we use Merkle trees. Rather than creating big lists, we use the hierarchical nature of time series data, which tends to be the largest data volumes we see, to aggregate metadata and actually do SHAs at those metadata levels and at every node in a tree, as opposed to just the leaf nodes. And this gives us orders of magnitude better performance, because we never have to explore trees that don't have changed Pshaws. So to put this a finer point on this, it looks like this, where we say, look, the Pshaws generated by the data of component A and component B, if those aren't changing, if we find a match of what we expect and what exists, all the way up at the metadata layer of the Pshot of 2019 data, we never need to explore any of the month or the leaf node day level of partitions for the Pshot because of the hit. It's only if they don't match that we actually have to go a layer deeper. And this benefit of doing the SHAs of SHAs, especially applied to Merkle trees and the rolling up of data and statistics like this, saves us tremendous amounts of time and gives us the ability to scale far beyond anything that would be a linear traversal of the partition space. The other thing that we do that gives us a huge amount of benefit and actually helps us optimize pipelines when it comes to scale is three really big important things. One is we do smaller jobs. We generate smaller jobs where we can generate a job per partition of data, as opposed to a job for an entire series of data. And this is a huge benefit that you largely can only do when you have the metadata that says you already know what the distinct inputs are for each output partition. And the benefit you get of this is that we can generate far smaller amounts of work. You get the benefit of having to do less shuffling and less moving around of data. And so you can actually have a far tighter mapping of the data and the work that's required, and as well as the resources. The second big thing that we do is we do intelligent persistence. And we're going to spend a bunch more time on this in a second. The intelligent persistence allows us to do smart caching for our pipelines that keeps copies of intermediate partition data. This means we never have to run the same piece of code on the same piece of data, which is a third piece. It means that we can always branch off and recover from intermediate stages. And it means that we actually are able to do less overall processing work, which means things move through faster, and we can build more pipelines that utilize our infrastructure even better. I'll talk about those in a quick minute. Jumping forward a little bit further here, let's talk about this last aspect, the self-optimizing aspect. Leveraging the data that we collect to do a lot of the tweaking and tuning we used to have to do. And at the core, one of the biggest things that this comes down to is the ability to automatically optimize needs us to do this intelligent persistence that I mentioned before. This intelligent persistence is built on top of a few fundamental core tenets. If we are able to store all of this incremental data as proactive caches, we can get a huge amount of really cool benefits. But it requires a few things. First, it requires that all of our components are immutable, or all of our fragments are immutable. If we're writing and rewriting fragments to the same place, we violate all of our constraints. And so it's incredibly important that our components are write once and only once. Even if we're retrying the same thing a second time, we still will generate a new UUID and make sure that it's right once. The second thing, we need the guarantee that all fragments are idempotent. If we apply the same input and transform logic together, we will always get the same output. In doing so, that gives us this incredible ability to say, well, if we've already done this before, we don't need to do it again. We can just use what we already have. The third piece is the ability to commit changes. By having a metadata layer that maintains the mapping of these components and their underlying fragments and their Pshots to the actual data that is being stored inside of S3 or GCS or AVS, this metadata mapping gives us the ability to actually commit changes and say that they are ready for downstream usage. It allows us to actually store a bunch more stuff inside of the object store and not necessarily expose it to downstream use cases until it's ready. This introduces the fourth part that is essential to intelligent persistence, which is the ability and the need to garbage collect. If we're writing a bunch of immutable fragments, at some point, there is a fragment that is no longer needed because it is a roll-up of some data that had a new calculation, but there is an abandoned fragment, just like how you get abandoned memory inside of the JVM. And you need a system to go behind and garbage collect to make sure you don't have any abandoned data that is no longer in use. So you have to be able to build these four elements into your intelligent persistence. But when you do, you get some pretty cool stuff. So to go a slight layer deeper on this, and then we'll visualize a little bit more of what this looks like here. But it really ends up creating a Pshot metadata to storage mapping. And the way to think about this is it's very similar to content addressable storage, where at a logical layer, I can have two totally distinct components that are in two totally different pipelines. But if they're performing the same operation, the same code and the same logic is applying to the same upstream pieces of data, regardless of where they happen to be sitting in my pipeline ecosystem, that Pshot, because of those guarantees we had above, now allows me to say, I no longer need to do this work. I already did this before. And in fact, I have it stored inside of S3. And in doing so, I can just use that. I don't even need to do anything different with it. It also lets me do things like atomic lists and reads and writes, where when I return the results, the list of all the underlying fragments of data, even if that component changes, if I have the list of partitions of actual fragments in the object store from a point in time, I know that that is a guaranteed snapshot of that data, regardless if new fragments have been generated and that component has been modified or mutated. I have an exact copy of that component from that point in time, which is incredibly valuable. And so what this starts to look like, if you remember our previous diagram here, this is the power of that location, which is all of the metadata that we have maps back down to this content addressable storage location inside of the object store that gives us all these benefits. And these benefits, to really put a fine point on it, become pretty profound. First, I get 0 operation pipeline copies. The replication of a pipeline is very similar to a Git branch. It is a metadata operation. I don't actually have to copy any data. I'm just copying references to the underlying data. Second, I get data deduplication across dev to stage to prod. Because of those guarantees around immutability and idempotency, I don't have to actually worry about if I have something in my dev environment polluting something in my staging environment, because the Pshot gives us the safety net. It tells us definitively whether or not it is the same thing. And so doing things like pre-warming pipelines in a staging environment and then deploying to a prod, for example, is literally just updating references to already existing data. Very similarly, that rollback and restart of pipelines becomes incredibly efficient because I'm just reverting at a metadata layer. Unless garbage collection has run and deleted the old unused fragments, my rollback period is just a metadata operation. Requires no new Spark jobs to regenerate work. I'm just updating my references to metadata and the underlying storage layer. And ultimately, what this means is we get faster, cheaper, and more efficient data pipelines that are easier for us as developers to maintain and use. All of these benefits coming back off of just that ability to immediate persist, which is built on top of the foundation of the Pshot, which gives us guarantees and assurances that what we're doing is safe. Now, I'm going to do a few quick of some of the other benefits, because this becomes really powerful once you have this intermediate persistence. First, actually, all three of them fit in this category. This intermediate persistence gives us some really great capabilities because we can access data from pipelines at any stage of that pipeline. So, for example, we can expose this content addressable storage supported metadata layer that gives us all of the dynamic mapping of any component that is an S3 compatible interface to the underlying object store. So even though I may be storing a bunch of files tied to their UUIDs and Pshots, by leveraging technologies like MinIO and their S3 gateway that talks to the metadata layer, that control plane, we can reconstruct dynamically entire file system paths based off of the metadata. We can do this and tell you exactly what is there without ever even having to talk to S3 because we have all the metadata there. And we can dynamically support multiple file path patterns because we know all the metadata. And then when reading the file, we just have to go look it up appropriately and talk to the object store then. So we get a really powerful S3 object store compatible interface to all of the underlying snappy compressed Parquet files, just with a cleaner, more logical interface. Second thing we get is a queryable API that we can talk to via our API, our SDKs, or CLI that lets us generate dynamic queries. We give two interfaces, this API and SDK, as well as a Thrift interface that talks to the Spark SQL Thrift JDBC interface that talks down to that same layer that says, when you initiate an ad hoc query against the underlying data of any stage of any pipeline, we can actually then go and look and figure out all of the from the metadata store, all of the partitions of data that's relevant to, and we can turn any stage of any data pipeline into a dynamic, queryable table without you having to do anything special. It's just there because we already are persisting the data and it's already available, and we already have a ton of metadata about it. So you get all these kinds of benefits for free that make it much easier for us as data engineers to rapidly iterate and prototype and profile data to figure out the next stage of the next transform to continue building our pipelines. As a quick recap, to make sure, because there's a lot of content in there, so hopefully everybody's absorbing all of this. 6 key questions. When we write data pipelines, we have to answer these questions. And when creating a declarative pipeline control system, the system itself must answer these questions. At the core, how do we answer these questions? We first have to track everything. So building a Dataaware system that continually tracks every piece of data, the work that's required, where it came from, where it went to. You have to be able to track a ton of data. Second, you need to be able to adapt and respond to changes, which means the system itself must be able to continuously evaluate and repair data that no longer matches what has been stored. That raises the third big need, which is we need to be able to do this efficiently. These kinds of calculations can be very expensive, and traversing entire partition spaces of big, large, complex pipelines can be very costly and expensive. So leveraging advanced capabilities and tricks around SHAs, Merkle trees, caching gives us the ability to cut out a lot of traversal that no longer needs to be explored. And then fourth, and lastly, self-optimizing. By leveraging metadata, we can get a huge number of benefits by persisting intermediate data. No different than how our web services like to cache data, or microservices cache data. We're doing the same thing for pipelines. We just have so much data that we can do it more proactively, and we get a huge number of benefits for it. And the key to all of this comes down to a pretty simple convention, which is the Pshot. The ability to do these recursive SHAs on the code and the data that is operating on. And at the core, this is the foundation. This is what tells us what we have stored today. Does it match what we need to have stored? And once you do that, you have the ability to create smarter pipelines with far less code. So thank you, everybody, for the time today. I hope you enjoyed listening to this talk as much as I enjoyed giving it. If you're interested in learning more, we have a ton of resources and assets at Ascend. We have some great white papers to read about this. If you want to play with our product, we have free trials and happy to give folks demos. And even more fun would be, we'd love to see you in our Slack channel. Come drop in, ask us questions. We're here to help. We love geeking out on this stuff, so we would love to chat with everybody and learn from your experiences and share our own. Thank you very much.